Hey everyone, thanks for coming. So despite the title, I won't tell you how to solve privacy problems. Instead, I will focus on a specific one, which is how to make sure that your model doesn't leak personal data that was used in training, of course, if you use PyTorch. So let me explain. This is an example of tabular data that was used by a governmental agency, and it's supposed to be anonymized because they removed personal identifiers, i.e. Name, surname, but this is anonymized until you have another data set that with some other categories can be linked with this data set. And this can be used by adversary party to learn new information about a person who was a part of this data set, which is not good. Another problem emerged when we started training large language models. So we thought that, all right, we mix all the data inside, we get some meaningless weights, and we thought that they doesn't contain any personal information until we managed to force the model to provide us personal information by some methods that described in papers. Another example, I think it is very important because it emerged as a way to make machine learning more private by letting users to keep their data on device. So it is called federated learning, and the idea is that you keep all your data on device, and the server which runs training only gets gradients to update the model and propagates back a new model to devices. So the devices run local training on their local data without exposing it to the server, and sends gradient to the server and get back updated model. And it sounded like a secure and quite anonymous way because you keep all the data on device, it never leaves the device until you realize that you can reconstruct the data from the model and from gradients. By collecting gradients, you can reconstruct exact images that were used during training. Wow, that's a problem. And there's actually many problems. So de-identifying, removing identifiers does not solve privacy. ML model weights memorize information, and even gradients used to train model, they can be used to reconstruct personal data. So we need something that covers all these cases and maybe even more. There is a concept called differential privacy, and it actually defines anonymization. It formally defines what do we treat as anonymous. And differential privacy is a property that a process can have. For example, if we have an operation like computing a statistic or training an ML model or generating synthetic data or whatever else that has data as input and something else as output, then the differential privacy property holds for this operation if the result of the operation doesn't change much when we remove one of the users from the data set. So if we change the user, the set of users, if we remove or add one user, we expect that the result is almost the same. Actually, we expect it to be the same, but it is basically the same, and it is defined in a probabilistic form. Not only differential privacy defines what is anonymity, it introduces a way to quantify how anonymous our processing of the data is. And it quantifies it with so-called epsilon. It's a number which has additive properties. So if we observe data set several times and apply some processes that hold some differential privacy, then this epsilon, this privacy loss, incurred by every single operation, they just sum up. And we can quantify the total loss. This is very convenient. And this anonymity is achieved by adding randomness. For example, if you want to ask a person a very sensitive question, you can ask them it directly, but very likely the person will lie. You can do another thing. You can ask them to flip a coin, and in one case say the right answer, in another case say wrong answer. So by doing this, the person have plausible deniability, so they can blame on the coin, and we'll never know what exactly their answer is. But by summing up the answers from many people, we can figure out what's the ratio of like positive answer on a question. And this is mathematically defined by this inequality. So we expect that if we know something about a specific user, given all the information we have access to, and if we have a likelihood of a property of this user, for example, whether they live in a certain place, this likelihood won't change much after us observing the process data, which holds differential privacy. And this likelihood won't change in extent of this E powered epsilon. So what I need to know is that by applying this DP to machine learning models, we can, first of all, we can publish a model which was trained on data owned by individuals without exposing their personal information, which may or may not used during the training. So we can also keep this model as internal, but clean of personal information just as a safeguard, right? To avoid any risks when many people are involved. And also we can prevent leakage of information when we do inference, i.e. when we ask language model something, we can be sure that it won't generate us personal information if it's anonymous enough. And lastly, we can do federated learning safely because we can anonymize all those gradients. We can anonymize all those models that are shared to the devices without exposing users' data to other users. And this is implemented with a modification of standard SGD by adding random noise to gradients. All right. So we have a framework for making models anonymous. How can you make your models anonymous? If you use PyTorch, we have a library, PyTorch Opacus, and I will explain to you how to start making your models anonymous. So just install this model, and the only thing you need to do actually is to create a privacy engine. It's a simple thing that encapsulates some information about what kind of privacy settings we expect, and it wraps your model, optimizer, and data loader into new objects that incorporate some stuff that will make your model private. So let's see what's going on here. So we expect that this model will be trained in 10 epochs, and we want to target to a specific epsilon, to a specific privacy loss, and not more than that. So we specify it here, and we let the library to make the rest, to calculate how much noise we need to add to the model. There is a hyperparameter that can be varied, and your privacy utility trade-off will be better if you find a good value. But the noise planning looks like this. You specify your privacy budget and how many epochs you have. And it gives you a new model, it gives you a new optimizer and a new data loader. And after that, you just use them in your PyTorch code and nothing more than that. So what happens here? What happens inside? To the model, we add some computation of per sample gradients. The idea of differential privacy is that we limit contribution of every single user to the model so that the model won't change much when we remove this user or add back, right? And to limit this contribution to the model, we need to compute per sample gradients. Instead of aggregating the batch and like sum it up in linear layers, in another layers, we need to decompose it back and limit contribution of every single example in a batch. And that's what is very annoying if you implement it by yourself, but Opacus does it for yourself, for you. So the optimizer adds DP noise on each step, which practically implements this DP SGD method based on the other optimizer that you use. So you can use Adagrat, any other optimizer, with some limitations, but not much. Just use it, just wrap it with the private version of it, and use it. And the data loader is also need to be changed, but this is to make sure that all the assumptions in the model, in optimizer, and in our privacy accounting on how we estimate this privacy budget are aligned together. So we need to make sure that the data loader picks at random samples with Poisson distribution, but like this is not a big difference in most of the cases. Here is a standard training loop. We have several epochs, and we just do standard PyTorch stuff. We iterate through batches. We do forward pass, then backward pass, then we do optimize step. You don't need to do anything, because if you use optimizer, model, and data loader that privacy engine gave to you, the DP noise will be added automatically inside this step. So everything is there. One thing that might be useful is that privacy engine also encapsulates accountant. Accountant is an object that tracks the privacy budget, tracks the privacy loss, how much exposure your model have, and actually limits it. So you just write your PyTorch code, and you get something like this. So you train, you get through epochs, and the loss declines. And the privacy loss, epsilon, it increases. It increases, and it can be limited. It can be planned. So you can specify what kind of epsilon you expect in the end. And this will guide you how much personal information is exposed. So what's under the hood? Under the hood, I described those parts, but practically these are like two substantial parts. It's a wrapper around the optimizer, which adds clipping this contribution of every single example to the model, and it also adds randomized noise to it. This is necessary to differential privacy property to be held for the model. And it updates accountant that, hey, I added this amount of noise, please calculate the epsilon, what we have right now. And another part, it is computationally kind of tricky, because we need to do this per sample gradients. In Opacus, we implement this by automatically detecting some basic layers, like linear layer, in your computational tree, and replacing them with the private version, with the version which computes this per sample gradients. And if we can do this, we just raise an exception. But more or less, all of the useful building blocks that are available in PyTorch, for them we implemented modules that can be replaced, and the replacement is done automatically. Another part that was implemented recently is we can, if PyTorch, functional torch can build, if you have a functional model, or you can do a PyTorch make functional of your model, then we can actually generate a function that computes those per sample gradients. And this can be useful if for your model we don't have a replacement that computes per sample gradients. And another thing is experimental, but it uses some low-level autograd things to compute per sample gradients by using some torch capabilities that my understanding are still experimental, and they're quite limited. For example, they don't support RNNs, LSTMs. Yeah, that's it. Those difficult parts are done for you, and you have this library, but how do you choose this privacy budget? How do you limit, how do you know what the value with which you need to limit your private exposure? Preferably, you need to use very low epsilons, like 0.1. In this case, theoretically, we guarantee that the likelihood of any event that you want to infer about an individual won't change more than 10%. So this is a very strict condition, and that would be great if we can use this low epsilon. So the model will be clean of any information personal. Only patterns that we can learn from many users. But this is not feasible practically, because when you do so, this ruins models' utility. So we'll just have bad models predicting bad things. And the pragmatic approach is to use the lowest possible epsilon that gives you acceptable utility. Let's see the examples. For example, Wikimedia, for their daily visits, they use epsilon equal 1. Apple, for their some health estimates, they use epsilon 2. Google for federated learning uses epsilon 6.9. US Census Bureau uses 19.6. But if we remember the theoretical definition of epsilon, it's a thing that limits our inference. And 19 in this framework is something that makes no sense, because if we compute what's the upper bound that we limit with this difference between model with one user and another, it's something that definitely more than 1, and this inequality makes no sense. It always holds, right? So what's the point? And it actually true for epsilon, for all epsilons more than 2 or 3, something like that. So what's the point? The point is that existing DP theorems that guarantees us that they provide us the upper bound of epsilon, right? So they don't provide the exact bound. And we believe that they greatly overestimate this bound. And probably the models trained with higher epsilons, because we add significant amount of noise still, they are much more private than we expect from the theorems. And the rule of thumb is that if we add DP noise, some significant DP noise, it is already much better than thinking about theoretical aspects of differential privacy. This is a practical consideration, right? Gray zone, gray area. But is there a lower bound, right? So we have a theory that gives us upper bounds, and we know that it is bad. Is there a lower bound? And yes. So the lower bound is how much privacy would definitely leak when we train a model with certain parameters. And yes, we have so-called membership inference attacks. It's a number of methods. How can we create a classifier that detects whether or not an individual data point was used in training or not. So this doesn't sound as impressive as reconstructing input data point, like reconstructing images that people use for training. But this is very close to the definition of differential privacy. And this is useful because if we guarantee that the membership inference attack is impossible, then automatically we can prove that the reconstruction attack is also impossible. And if we can do reconstruction attack, then definitely we can do membership inference attack. So this is very useful. And there are many methods that we can run on our models, and even libraries that you can just check out. One is also developed by Facebook for PyTorch. Another one developed by another lab for PyTorch TensorFlow. And this can give us this absorbed privacy leakage that can that have a potential of being a way of calibrating the epsilon that we use to limit our model's privacy. So that's it. If you want to train your models with privacy, use Opacus. If you do research, especially in the fields with sensitive data, with privacy attacks, many people who like works on privacy attacks, they use Opacus to check their attacks. Also contribute to the library, it's open source. That's it.